Yeah, thanks a lot. Michael, I'm really happy that I can be on the stage today to show you our use case from the automotive industry that we've been working on together with Kipu Quantum for the last couple of months. Our use case is called modeling heat flow in automotive industry. We'll go a lot deeper into it. But before we dive into the use case, a few words about Schaeffler. I'm not sure whether everybody knows what we're doing. We're an automotive and industrial supplier, supplying all kinds of parts and subsystems that enable motion in some sense. And motion is the combining element of our 8 product families, shown here on the left-hand side. So you may ask yourself, well, what has quantum computing got to do with the, typical mechanical engineering or automotive supplier? And the answers are here on the right, actually. There's multiple areas where we believe that quantum computing may give us an advantage, may give us a competitive edge in future. And that's why we are exploring that technology together with partners. Our main aim is to learn about quantum computing. That's where we are selecting use cases that we understand well, and where we don't necessarily expect a transformation, as Lucas just mentioned, but where we expect a good outcome with respect to solutions of quantum computing. We selected Kipu because we needed a partner who's really honest, open, and who's also willing to educate us when it comes to quantum computing, because we want to fully understand what is happening behind the scenes. So without further ado, I give you a quick introduction to the use case itself. Heat modeling or thermal management modeling is a typical engineering problem which is governed by differential equations. It is a problem of a class that is very common in our R&D. It's not only thermal management, it's also a simulation of motion, it's a simulation of production processes. It's all kinds of simulations that fall into the same problem class. We've chosen this one because we fully understand it, because it's very scalable, and the dynamics are not that fast, so that we expect a good solution using quantum computing. The aims of the project was to reformulate these heat models or these differential equation systems in a way that they can be executed on a quantum computer. We then wanted to implement those algorithms on simulators and also on real hardware. And finally, if the results are good, we also want to make those algorithms, those methods available to our engineering teams. But above all, as I mentioned before, we wanted to learn about quantum computing and the algorithms. For the visual people amongst you, here's a picture of the use case that we've been working on. This is this power electronics module. There are some transistors mounted on it, and these transistors, they heat up during operation, so that the colors are basically representative of the temperature. During the engineering phase, when we optimize this module, we use FEM with models with 100,000 to millions of degrees of freedom. And then once it's sufficiently optimized, we reduce the models to an order of magnitude of about 8 to maybe 64 degrees of freedom to let them run on the microchip during operation of the car or robot or whatever, so that we have some sort of online heat management on the device itself. For the quantum computing problem, we're first focusing on this very small, very simple system down here. It's basically just a first order ordinary differential equation with limited amounts of degrees of freedom. That can be solved on a calculator in real time. So it's not a particularly difficult mathematical problem. But it gives us an idea of how quantum computers perform for these types of problem classes before we then in future want to scale it up to maybe that sort of size, and in the next few years maybe even bigger, at which point we then expect an advantage with respect to quantum computing. How it's done, how we've implemented this system of equations down here is now explained by Gernot from Kipu. So I hand over this presenter to him, and yeah,
thank you.
Stage is yours.
I will give, it's still a running project. I will give you now a little bit insights and some preliminary results of the project. And there essentially I will, let's say, finish with two main conclusions, with two take-home messages. And the first one is already comprehensively outlined here on this slide, is a quantum journey does not start with quantum, it starts before. Many use cases of which we expect that quantum computing, a quantum solution, will be useful are not necessarily quantum by nature, right? So, and that's pretty much the case for this partial differential, or for this ordinary differential equation. Here I showed in comparison with the time-dependent Schrödinger equation. That's the type of equation you need to run it on a quantum computer. And the first step decides how we reformulate that problem to make it quantum. That's the mathematical reformulation. I also like to call it the pre-processing step. And there are different strategies that you can follow. They are not necessarily standard, but some of them are also well known. And this is the first thing that we did also for Schaeffler, was this mathematical reformulation of the original classical problem into something that looks like a quantum approach. We can follow, we have highlighted here two different ways how we can do that. We could either reformulate that problem directly into something that looks like a Schrödinger equation or time-dependent Schrödinger equation, as shown here. And then we can follow with an approach that is already formulated by Feynman and Kitaev. It's called the Feynman-Kitaev Hamiltonian. And that requires a history state of the wave function. So we would store essentially all information over time and generate that on a quantum computer. It has the advantage that this method is not iterative in time. It's global in time, but it has a disadvantage that the smaller this time discretization is of the problem, so the more I want to resolve the problem in time, the more qubits I will need. The other formulation that we followed is that we reformulate this equation by a Chebyshev representation, then we end up with a set of linear equations, and that is a problem that's pretty well studied already in the community. And you may have heard about the HHL algorithm, and that promises an exponential speed up for solving those problems in comparison to classical computer. However, it requires a fault-tolerant quantum computer. There are also other approaches like QSP or AIDAQ protocols, and that's also what I will show you later. It is a very universal character, so that means that we could also use other ODEs for it and solve it in this manner. The method is global in time, but we will end up with something that's called a matrix and this associated condition number, and that stands for the complexity of the problem, and the quantum approach or the quantum resources will scale accordingly with this complexity. So I'd like to highlight a little bit in this direction of the Chebyshev representation, because so far that's the one we have most of the results already generated. So what we do is we approximate, let's say, the function x of t with a Chebyshev. We expand that with coefficients. And now the job is essentially to find these coefficients in this expansion. This can be written in this kind of set of linear equations where L is a matrix which is known and B is a vector that's also known. Our job is essentially to invert the matrix L, and there are different protocols already existing. Usually L is not necessarily a Hermitian, so we have to do some additional steps to make it quantum ready, but this is it's a minor thing here. And then essentially there's a possibility to deduce a target Hamiltonian that is associated to L and B. There's also a standard protocol existing, and then you are left essentially with the choice of the quantum algorithm that you want to run. And that is what I'm showing you here, is a comparison, a benchmark. At the moment, I think this is for a condition, for a low condition number, I think it is 1. So it's the complexity is not too large. It's a matrix 16 by 16, and the whole problem corresponds to 5 qubits. So you would need 5 qubits to represent that. So and if we compare this with different adiabatic protocol, for instance, would require 10 Schlotter steps to implement it on quantum hardware. The number of Schlotter steps is associated with the circuit depth, so with your program length. And that's something that is limited what you can implement on current NISQ devices. So this is very essential to also use a current quantum computer to essentially run this kind of circuit. We also have different algorithms which are based on adiabatic quantum computing, and they require much less resources, quantum resources, and they are, let's say, ready to run on current devices. QA-OA, this is a kind of standard algorithm you see. We have been implemented a version with 7 layers, but we did not achieve the fidelity that is necessary to solve the use case and make it ready for the application. So the fidelity here, the target fidelity was 97%. Gives us a feeling for the accuracy of the solution that you can achieve with such an approach. Okay, and here what you see here is how adiabatic quantum computing scales, not with the size of the problem, but with the complexity, when we increase the condition number. That's something that can easily happen, right? So you want to have a universal approach. You don't want to care whether you have a very complex problem or a lower complex problem. That's why it's very important to look at this. And this is also the kind of, let's say, more negative thing, is that the quantum resources in this approach will very much depend on the complexity of the problem you're looking at, not necessarily the system size. So you see, when we scale up the condition number from 1 to 1,000, which are all realistic scenarios in the application, you would require an increase of your quantum resources by a factor of 10. So make it the quantum circuit 10 times longer. And this is an aspect that's very important for the engineering of quantum algorithm. That's where you start really looking into the algorithm, developing new protocols, new approaches on a very algorithmic level that is suitable really for the current hardware. So, but anyway, before you can do that, you have to look at the pre-processing step. A few highlights. This is what I wanted to tell you in the first place, that it is very important before you do anything with quantum, look at your use case. How you can essentially make it smaller and still have you make something useful with it. It is very important that we follow different protocols in the reformulation of the problem, because that will decide also how you can use quantum computing, how many resources you will need, how good the solution will be. The Chebyshev spectrum method is a promising path to solve such problems here. And we have now estimated only from hardware benchmarks or from the hardware roadmaps what is expected in the next few years, that the practical implementation for use cases they are currently run at Schaeffler, it will take 2 to 3 years without making any improvements on the algorithmic level. So there is a lot of things that we can do additionally. And then my estimation is if we continue working on this, it takes just another year to make matrices or to cheat matrices of a size 100 by 100 or 200 by 200. Here the Feynman-Kitaev history state is something we are currently looking at. The project is not finished. We are happy to report on this at a later point in time, but we will see how this is going to help us also to bring here useful application at work. Okay, this is essentially regarding this application. You have different possibilities, also a little bit commercial now and marketing for us. So we have different possibilities to collaborate with us. You can scan here this QR code and learn more about us, and we are very happy to talking to you, particularly because we are also, my personal view is that it's very important that the quantum ecosystems gets exposed to use cases which have an industrial relevance. It's not foreseeable which of them we can really solve with a quantum computer. For this, you need to collaborate with experts from the quantum field. And in this way, we both can learn how to make quantum computing useful, right? And we help you, for instance, with a full stack approach to realize this. Okay, with this, I think Michael and I would like to thank you, and we are looking forward to questions if you have some.